Here's an example solution of one of the problems in homework for section 2.2. This is number 2, I believe. Write that down here. So number 2 from the homework for section 2.2. And these first several problems are very similar, and so the computer will just sort of generate, questions as they go. I'll try to just answer sort of the general stuff all at once. The question is asking us to find extreme points, inflection points, where the graph's increasing, decreasing, or concave up or down. And so it's a little weird. It's asking the things sort of out of order. It makes more sense to first do our sign chart to answer the second question, where it's increasing and decreasing and concave up and down, and then from that it's really obvious where the relative extreme points happen. So I'd recommend answering, since you know what's coming, answering the increasing, decreasing, concave up, concave down question first, and you'll get to enter it at some point, but then you'll know for sure that your first answer is right. All right, so here we go. So we know that to make a sign chart for first derivative, we first need to calculate the first derivative, so I'll go ahead and do that here. That's 8x squared minus 24. And I know in my heart that I'm going to need the second derivative as well, so I might as well just put it all up here where I can refer to it. Notice that I'm labeling everything I'm doing. I have f of x equals, I have f prime of x equals, and I have f double prime of x equals. And so now I know that when it asks me a question, if it's a question about slope, I know to use f prime. If it's a question about y coordinates, I'll use f. And if it's a question about concavity, I'll use f double prime. So knowing I need to do with all those things in advance is good. And labeling them is really important, or you won't remember what to put numbers into. All right, so the sign chart for first derivative, we build by first finding, I guess I don't need to write that again. We build by first finding where the first derivative is equal to 0. So we set our first derivative equal to 0, solve for x, so x squared. Oh my gosh, did I just say that 3 times 2 is 8? Good Lord. Sorry, 3 times 2 is 6. So sorry if you hope you didn't pause the video before you found out that I was, before I messed that up. Yeah. All right, so this is a 6. Okay, so that's better. So 6x squared minus 24 equals 0 is the same thing as x squared equals 4, which means that x is plus or minus 2. So that's our first step, and that's what we called our critical values. So that's how we referred to those. When we build a sign chart for f prime, we are going to label some values of x. We want to make sure that our number line includes the critical values. So I'll put little marks here. So these points are the critical values. And I want to label some points in each of the areas. So I'll label minus 3, 0, and 3. And so now I want to label my sign chart with whether f prime is positive, negative, or 0. And so that's why I've written down here f prime to remind me that that's what this is for. It's important to label this because we're going to draw another sign chart for f double prime in a second, and if we don't label them, then you're likely to be, not likely, but you may use the wrong chart for the wrong question. So label everything you do, especially when there's more than one thing running around on the page. So to label this, I'm going to evaluate f prime of negative 3, f prime of 0, and f prime of 3. And for each one of these, I'm talking about f prime values, and so remember my f prime formula, now that I fixed it, is here. So if I put negative 3 in for x, this will be 6 times 9 minus 24, that's 30. So what I really care about is that that's positive. When I put 0 in, that's super easy to do. Putting 0 into f prime gives me negative 24. And all I care about is that it's negative. And when I put 3 in for x, again, I'm going to get 30. Think about it, it should be the same thing because it's being squared as it was for negative 3. So I have positive, then negative, then positive. That means that my f graph, and I didn't give myself enough room here, but my f graph is going to be going up. So up arrow means it's increasing. The f graph will go down and then go back up again. So I know the basic shape of the f graph, so I'm labeling f, is that the graph should be going up until it gets to negative 2, down until it gets to 2, and then up again forever after that. So that's the answer to where my graph is increasing or decreasing. And I'll do a little inventory of this on the next slide. I want to put my second derivative stuff on here as well. So that's enough information to answer the question about where is the graph increasing and decreasing. I can see it here, increasing, then decreasing, then increasing. And then the question about where I have the extreme points, I can see that from this graph as well. At -2, when x is -2, I should have a high point. You can see the graph stops going up and starts coming down. So that -2 will be a relative maximum when x is -2. And when x is +2, I'll have a relative minimum. And so it's not exactly what they're asking for. They want to know the whole coordinates, so we'll come back to that. But I can see everything I need to see from that sign chart relative to the increasing, decreasing question and the extreme value question. For the second derivative, I go about making my chart the same way. This time I'll make it a little lower. I've learned from my mistake. X coordinates down here. What I need to know for the second derivative sign chart is where the second derivative is equal to 0 or undefined. And so for my second derivative, it's super simple. It's just 16x. The only place that's equal to 0 is when x is 0. So x equals 0 is the only place where the second derivative might change sign. So if I put a couple other values here, give me something to try, it's not hard to tell that f double prime of -1 is -16, so that's negative, and f double prime of 1 is +16, so positive. So again, the f graph, I can sort of write down what it means about f. F will be concave down for values of x up to 0, and then will be concave up for values of x greater than 0. So that answers my concavity question, where my graph is concave up and concave down. My graph is concave down up to 0 and concave up from 0 on. And you can see that there's a basic consistency between these two pictures. The f prime analysis tells me I'm going up and then down and then up. The concavity analysis tells me my graph is concave down and then concave up. And so you can sort of imagine a graph that will have both of these properties. Right? These are really all about the same picture. So these two pictures are very consistent with each other with a graph that's got this kind of shape, okay, regardless of which picture we use. All right, and so that allows me to answer all of the questions that are on here. I didn't answer them, but I will on the next slide. Also, this is an inflection point. So at x equals 0, we have an inflection point. Inflection point just means that your graph has changed from concave down to concave up, or the other way around. As long as the second derivative changes sign, negative to positive, positive to negative, then technically that's called an inflection point. Okay, so here's the inventory. Let's go. We found that f is increasing on the interval -infinity to -2, and then later it's increasing on the interval 2 to infinity. F is decreasing at the other values, so the interval -2 to 2. Remember, this is not a point, this is the interval from -2 to 2. I don't say at a point, I say on an interval. So it's all context dependent, but this notation is the same, but that's the interval -2 to 2. In other words, all the x values between -2 and 2. We said that f has a relative max at the point where x is -2. So at the point -2 comma whatever the y value is. The reason we know that's a max, remember, was that we said the graph was on its way up until you get to -2 and then on its way down after -2. If you refer back to the previous picture with increasing and decreasing with the arrows, you can see that we have a topping out point at -2. What's the y coordinate? Well, the y coordinate, remember, comes from plugging -2 into the original formula. The original formula is the thing that tells us the y coordinates. The first derivative tells us slope, the second derivative measures concavity, and the original function is a measurement of the y coordinates. So did I actually do this? I guess I didn't. Hang on a second. All right, I'm back, having gotten my calculator. So f of -2, the number that goes here, if you put -2 back into the original formula for f, it looks like we get 27. So the point -2 for x coordinate, 27 for the y coordinate, is a topping out point, a relative max. F has a relative min at the point, well, we know the x coordinate's 2. We know the x coordinate's 2 from what we wrote on the previous slide, And so the y-coordinate is just f of 2, whatever that is. So we can plug 2 in for x into the original formula, and we get negative 37. So at the point with x-coordinate 2, y-coordinate negative 37, we'll have a relative minimum. Our concavity analysis said that our graph was concave up. Remember we said the graph was concave up to the right of the inflection point, so the right of 0. So on the interval 0 to infinity, and f was concave down on the interval minus infinity to 0. So again, go refer back to the little sketch that we drew above the f double prime sign chart. Tells us all about the concavity. Therefore, at x equals 0, we can see that the concavity has changed, and so f has an inflection point at the coordinate 0, whatever f of 0 is. So I got to plug 0 back into the original formula. F of 0, I've lost track of my f altogether here. Oh yeah, so f of 0 is just negative 5. So x-coordinate 0, y-coordinate negative 5 is going to be a point on the graph. So so now I know 3 particular points, these negative 2, 27, 2, negative 37, and 0, negative 5, that are significant on this graph. They're the high point, low point, and then the place where the inflection changes. So the last part of the problem is always to pick out the graph, but you're picking it out of a lineup, so it's not too hard to do. Usually just one piece of information is enough. The increasing decreasing is easier to look at, I think. So we want something that goes up from negative infinity to negative 2, and as soon as you're looking for that, there's only one graph that even does that. This graph is the only one, so D is the only one that is increasing from negative infinity to negative 2. If we look at the rest of the analysis, it's going down until you get to 2, it's going up again, so that fits our increasing decreasing analysis. It fits our concavity analysis. You can see that the change of a concavity is happening somewhere in there, so it's very believable that that's at x equals 0. It's hard to see concavity changing, but you know about where it's happening. And if we were to touch the little magnification glass and zoom in on it, we should see that it really does hit these. These coordinates, but it's the only one that even has the right shape, so that's got to be it. Notice that when I did this analysis, I used my sign charts first so I could answer the increasing, decreasing, concave up, concave down question, and then from that, it's very easy to answer the question about relative max and min and inflection points. So I would really recommend doing it that way instead of trying to do it in the order that the questions are being asked. The real question is to do all of those things, but it's having you enter it in a way that, in my opinion, is backwards. That you really don't know, you don't need to know the relative max and min and inflection points before you have even decided where the graph is going up and going down. You should be doing it in the other order. Anyway, that's how you get all the answers to those questions.